All right, so today we're diving into some pretty cool math,
Yeah.
inverse trig functions and
Yeah.
their derivatives.
Yeah. It's going to be fun.
You sent us this audio lecture in Korean,
Right.
which is a little intimidating.
It's a fascinating topic.
It is fascinating, but don't worry, we're gonna break it all down and get to those aha moments.
And you know what's amazing is that even in like advanced math, like calculus,
Right?
the most elegant solutions often come from understanding those basic relationships
Hmm.
from trigonometry.
Yeah. Okay, so let's maybe start with something that's familiar, I think, to a lot of people.
Okay.
Sine and cosine.
Right.
And I like to think of these, picture a Ferris wheel.
Yeah, the classic Ferris wheel.
Right, because that's really the best way, I think, to visualize what's going on.
Yeah.
So as you're going around the Ferris wheel, your height's changing, right? Up
Yeah.
and down, up and down.
Exactly.
And so, like, sine is essentially tracking that vertical movement, that up and down, and cosine's kind of keeping track of your horizontal distance
That's right.
from the center.
It's like sine's watching your up and down dance, and cosine's got its eye on your side-to-side sway.
Okay, yeah, I like that. And they just keep going, right? Like the Ferris wheel.
Like, round and round.
Full circle, and then it repeats.
That's why we get that wave-like graph.
Precisely. That's the beauty of it.
Okay, so now imagine you're at the top of the Ferris wheel.
Okay.
We could use sine to figure out your height.
Right.
No problem.
Easy peasy.
But what if we wanted to go in reverse?
Okay.
Like, what if we knew your height and we wanted to know the angle of the Ferris wheel?
Uh-huh. That's where our friends' inverse functions come in.
Okay.
Arcsine, arccosine.
Right.
They help us answer those going backward questions.
So it's kind of like the reverse button on your calculator.
Exactly.
Instead of putting in the angle and getting the ratio.
You put in the ratio, out pops the angle.
Like magic. But math magic.
Exactly.
Which I guess is even better, right?
Right.
Absolutely.
Can I just clarify something?
Yeah, of course.
Arcsine, inverse sine, those are the same thing, right?
You are 100% correct.
Okay.
They are the same thing.
Right there.
Arcsine is like the shorter, cooler nickname for inverse sine.
Okay.
But they both represent that same idea of going backwards.
Okay. Now, I'm very visual, so you mentioned something earlier about graphs and reflections. Can
Yeah.
we dig into that a little bit?
Absolutely. So picture the graph of the sine function.
Okay, got it.
Now imagine you're holding up a mirror right along that diagonal line, that line yx.
Okay.
The reflection you see, that's your arcsine graph.
Hmm.
The input and output have literally switched places.
They've flipped.
Exactly.
Okay, interesting.
It's pretty neat.
But we can't just let those graphs,
Go on forever.
go on forever. Because I know there's something about a restriction and the domain of sine and cosine.
You're absolutely right. We can't just let them wave on forever. Because remember, for a function to be a function, every input can only have one output.
Right.
So it's like saying each height on that Ferris wheel can only correspond to one unique position during that single rotation.
Hmm.
We restrict sine and cosine. We pick that sweet spot on their graphs where every height matches up with only one specific angle.
I see.
And that makes sure arcsine and arccosine behave themselves, give us one and only one angle as their output.
And that makes them much more useful.
Exactly.
Okay, so we've got our Ferris wheel, we've got arcsine, arccosine, these like reverse buttons figured out.
Right.
But now we're bringing in derivatives.
Yeah, buckle up.
Because this is where it gets really interesting to me, at least.
This is where we find out how quickly things are changing.
Yeah, and how those changes relate to each other.
Exactly. We're talking about the rate of change of these inverse trig functions,
Okay.
which, if you're thinking about a graph, it's all about the slope of that tangent line at any given point.
Okay, got it. But I gotta be honest with you.
The first time I saw the derivative formulas for arcsine and arccosine, like my brain, it hurt a little bit.
I can imagine.
Square roots, fractions, it was a lot.
It's a bit more visually complex than the regular sine and cosine derivatives, that's for sure.
Right.
But there's a really beautiful logic behind it all, I promise. It's
Okay.
all connected.
Well, I'm always up for a good aha moments.
Oh.
So
Okay.
let's unpack one of these derivative proofs, not get too lost in the weeds, but at least try to understand the core logic,
Absolutely.
maybe with some visuals if we can.
All right, you mentioned arcsine earlier.
Yeah.
And I think that tends to be the one that causes the most head scratching.
Okay.
So let's go with that one.
All right, let's unravel the mystery of the arcsine derivative.
Okay, so remember we talked about that mirror image thing with the graphs?
Yeah, with the reflections?
Exactly. That reflection is key to understanding this whole derivative thing.
Okay.
So picture this. You've got your arcsine graph, right?
Now imagine you draw a line that just grazes that curve at a particular point. That's our tangent line.
Okay.
Now, because of that mirror image relationship, there's a corresponding tangent line on the sine graph as well.
Oh, interesting. So two tangent lines, one on each graph, mirroring each other.
Exactly. And here's where it gets really cool. The slopes of those two tangent lines are reciprocals of each other.
Mm.
So if the slope of the tangent on the sine graph is, say, 2, the slope of its reflection on the arcsine graph would be 12.
Whoa. So those mirror images aren't just pretty to look at.
No, they're not.
They actually tell us something about the slope.
They hold the key.
That's pretty cool.
It's pretty neat, right? So how do we actually find those slopes? Well, that's where derivatives come in.
Okay.
We can express the slope of the tangent on that sine graph using the derivative of sine, which we already know is cosine.
So cosine's in the mix here.
Oh yeah, cosine's a key player.
Okay.
And here's where we get a little trigonometric. Remember that Pythagorean identity? The one that connects sine and cosine?
Yeah, vaguely.
We can use that identity to basically swap out cosine
Yeah.
for an equivalent expression involving sine.
Okay, it's like a substitution.
Exactly, like swapping one ingredient for another in a recipe.
Right.
But here's the thing. We're trying to find that slope on the arcsine graph.
Right?
So we take the reciprocal of that whole expression, just like we talked about with those mirroring slopes.
And that gives us the derivative of arcsine.
Boom. There it is.
That square root, the fraction, it's not just some random math torture device. It's a consequence of that reciprocal relationship.
Precisely.
And a little trig magic.
A little sprinkle of trigonometry never hurt.
Never hurts. Okay, so we've covered reflections,
Right.
reciprocals.
Kind of trig magic. I feel like I need like a math refresher course or something.
But the coolest part is there's even more to uncover.
Okay.
Remember we were talking about how sine and cosine, they're connected, right?
Right.
Well, there's this amazing identity that shows this hidden symmetry between arcsine and arcosine.
It's like they're secretly best friends, always working together.
All right, you got to tell me more about this. What is this secret best friend identity?
It's actually pretty straightforward. Arcsine x plus arcus x to 2.
Okay.
So what that means is if you take any value of x between -1 and 1, plug it into arcsine, plug it into arcosine, add those two results together, you always get 2.
So no matter what, 0.5 minus 0.2, 0.999, it all adds up to 2.
It's like a mathematical magic trick. But
Yeah.
it's not magic. It all comes back to that relationship between sine, cosine, and their inverses.
Can we bring back the Ferris wheel? Is there a way to kind of visualize this with our Ferris wheel?
Oh, absolutely.
Yeah.
So imagine no matter where you are on that Ferris wheel at the top, halfway up, even those weird in-between angles.
Right.
The angles formed by your position relative to the center.
Okay.
When combined, will always add up to 90 degrees, which is 2 radians.
Hmm.
So it's like no matter where you are in that cycle, those angles complement each other to make a right angle.
Yeah, that's pretty wild. What about the proof, though? How do you even begin to prove something like that?
The proof is pretty elegant. It uses trig identities, the relationship between sine and cosine, and that connection between a function and its inverse.
So it all ties together.
It all comes full circle.
I like it. I have to say, I came into this thinking, oh, inverse trig functions, this is going to be rough.
Yeah.
But you've actually made it, I don't know, kind of awe-inspiring.
That's the beauty of math.
It really is, though. Who knew there was so much, I don't know, elegance, I guess, behind all these formulas?
It's about looking beyond the surface because sometimes the most complex looking problems have the most elegant solutions.
Well said, well said. And I think that's a good place to leave it for this deep dive. So for everyone listening, the next time you see a formula that looks a little intimidating, don't panic. Remember, there's often a lot of beauty hidden beneath the surface. Just channel your inner mathematician, maybe picture a Ferris wheel, and I bet you'll start to see those elegant solutions too. Thanks for listening.